In this video, we'll go over query processing. So we'll specifically look at how a given query is first translated and then sorted, and the different kinds of operations are applied on top of it. So basically, the database management system has its internal processing that's applied onto a query. It starts out by scanning the entire query and identifying different tokens in the query. Then there is a parser that basically checks the syntax of the query, and then there are validation checks that happen on all the attribute and relation names that are used in the query, and then a query tree or a graph is created that's then used to come up with an execution strategy, so that the most optimized strategy can be used, and then that query plan is finally executed. So that's what happens behind the scenes after you've written your SQL query, and the query is fired. Before it actually looks at the entire data and returns the result. All of this processing happens with that query behind the scenes that's managed by the database management system. Query optimization basically involves with looking at different kinds of execution strategies and then choosing the best one so that it's efficient and the results are returned as quickly as possible. This strategy cannot be the same for all queries. It just depends on the type of query and how many joins are there, how many nestings are there, and what kind of relations are being referred, because some relations could be small, some could be really large. So it all the optimization techniques applied varies based on that query. So here are the typical steps, high level processing steps. So basically we start out with the query in our high level language like SQL, which is a declarative language. So we write our declarations of what's the kind of data that we want to fetch. So that query is taken and it's scanned, parsed and validated. So all of the tokens are pulled out of it, the syntax is checked, and then all of the relation and attribute names are checked. Once that's done, then it's passed on to a query optimizer, which then comes up with an execution plan, and then that execution plan is passed on to the query code generator, which then executes. It does the execution of the query, and then it's passed on to the database processor, which finally returns the results of the query. So the execution could be done directly, which is an interpreted mode where the query is just interpreted and the results are returned, or there is the compiled mode as well, wherein the query is stored and it's compiled and stored and it's executed later when needed. So this the execution can happen in two different ways, directly or after compilation, depending on our needs. So what happens is, the very first thing is the translation. The SQL queries are taken and they are translated into relational algebra, which is the underlying theory anyways, and all of the other operators that are needed. So basically what that means is we have our SQL queries, which are in this select from where expression style. That's how they're written. You have these blocks, select from where, and then there's optionally group by, having, and sort constructs. So that's our basic, those are our basic units, and each of these units are then translated into relational algebra operators. So here's an example of how the translation happens. Suppose here's our SQL query. What we want is, we want to select first name and last name of all employees from the employee table where whose salary is greater than the max salary that's received by employees in department number 5. So that's what we're interested in. So you see that there is an inner query in this case, which is selecting the max salary of from the employee table for those employees that are in department number 5. So that inner block is this inner query, and then our outer block is basically then fetching the last name and first name of employees whose salary is greater than whatever we found in the inner block. So now, so basically the query is broken down into these blocks, and then for each block, then there is a corresponding translation that happens into its corresponding relational algebra expression, and that's what you see over here. Now the inner inner block is translated into, so we use extended relational algebra here, which has further operations to support aggregation and counting and such. So we use the extended relational algebra here. So basically we want to select from employee relation all tuples where department number is 5, and on that we are applying aggregation to fetch maximum salary. So that's our inner block translation. And then once we have that, our outer block translation is basically whatever the result of this is, say it's C, then we want to do a selection on employee where salary is greater than C. And then do a projection and get just the first name and last name. So that's how our entire query, the inner block, outer block, got converted into its corresponding relational algebraic expressions. And then the query optimizer, once this is done, it will basically choose an execution plan for each query block. And then that execution, the most optimized one, gets applied. Now there are additional operators to handle different kinds of clauses that are there in SQL. Semi-join and anti-join are two of those additional operators. Semi-join basically takes care of it's used to do unnesting. So whenever in SQL you have nested queries using exists in any, so when you have subqueries that use these clauses, then that's where semi-join construct is used. Here's the symbol for it. So basically the syntax is we're comparing two tuples T1 and T2, and we want to compare their x and y attribute. We're going to use a semi-join operation. What it means is, now T1 is the left table, T2 is the right table. So what this means is a row of T1 is returned. So it's basically we're going to start with the first row of T1 and the first row of T2 and compare their x and y values. Now a row of T1 is returned as soon as T1.x finds a matching value of T2.y. And then we don't search any further. So that tuple is returned, and then we move on onto the next tuple of the left table. So we search in T2 only until we find a matching value and then stop, and that's the reason it's called a semi-join. We don't look at the entire table. And then there's anti-join, which is kind of the opposite. It's also used for unnesting, but specifically to handle not exists, not in, and all queries. So basically here's our symbol for the anti-join. So again we have our T1 and T2, which are the left and right tables of the anti-join. The way this works is we are again comparing the tuples of T1 and T2. A row of T1 is rejected. Now in the previous case we keep the row. In this case the tuple is rejected as soon as T1.x finds a match with T2.y. So as soon as first match is found, then we don't do further processing. That row is rejected. We move on into the next row of the left table and again start comparing with the right table. The moment a match is found, that row is rejected, and so on. So it's basically to take care of the not exists, not in, or all kind of subqueries. Now internally for query processing, external sorting is needed. Basically it's used a lot. It's often used for a number of different kinds of operations like joins and for projections and to calculate different set operations. So basically the purpose of external sorting is this algorithm is used for large files that don't fit entirely in the main memory. So there could be some tables that have lots of data, so there's really large data and it cannot be pulled into a single file for processing when it's brought into the main memory. So that's where we need these sorting algorithms, and sort merge strategy is what is used. So it's based on sorting, so breaking up a large file into smaller subfiles and sorting them individually and then merging the sorted runs. So that's the idea over here. And what it uses in here, it uses the main memory. So there is a set buffer space in the main memory that's allocated to the DBMS to do this processing. So basically the database management system has a cache and that uses this buffer space. So here's the sort merge algorithm that's used for external sorting. Now say we have a large file. So typically the file is broken up into multiple blocks. So this two phases in here, we want to determine how we break up a huge file into subfiles and then sort each of those subfiles, and then we need a strategy to merge them, and we have to do all of this in the given buffer space that we have in the main memory. So say we have a large file and it's broken up into multiple blocks. Say there's 1024 blocks in the file, and then the available buffer space, basically the given buffer space that we have can handle 5 blocks at a time. So what we will then do is, so a number of subfiles or runs will be basically the 1024 divided by 5, so we need about 205 subfiles. So the sorting phase involves breaking up into the 205 subfiles and then sorting the records in each of those and then storing and writing them into a temporary subfile. So what we'll end up with is these 205 subfiles. Then and each of them are sorted, but now we need to merge all of our sorted results. So next comes the merging phase, where what we need mainly over here in the merging phase is a degree of merging. So how many files can we merge at a time? Because again, this depends on the buffer space that we have, and we earlier said that our buffer space can only handle 5 blocks at a time. So the degree of matching always has to be smaller than that buffer space. So because we can handle 5 blocks in the buffer space, our degree of matching is set to 4, because when we are doing the merging, we need to reserve 1 block to write our results, the output of the merging. So we reserve 1 for that, and then we're going to handle 4 subfiles at a time. So basically what this means is, in the merging phase, what we do is we take the 205 subfiles that we have and then merge 4 at a time. And what we end up with is we take the 205 and merge 4 at a time, so we basically end up with 13 files after that first pass. Then we take those 13 files again, merge them 4 at a time, and we end up with 4 files. Then we merge those 4 files into 1 file, and that's how there's one big sorted file. So that's the general outline for the sort merge algorithm that's used extensively in a number of other algorithms when query processing is being done. So basically, like I said, the degree of merging is basically the number of sorted subfiles that can be merged in each step. And then the performance of this algorithm is basically the number of disk block reads and writes that are being done that were performed once the sorting has been completed. So the query processing now needs algorithms for the different operations. So there's select operation, there's project, there's join operations. So for each of them, it then needs algorithms to handle those operations. So basically, search operation, what it involves is locating records in the disk file, and then they have to satisfy a certain condition. So this involves basically scanning through the file and pulling out those matching records, or using an index scan. If there's indexing provided, then doing an index scan and pulling out those relevant searches or the relevant rows. So there are different search methods to perform a simple selection when there's a simple condition. There's a linear search, which is the most simple brute force algorithm, where you basically look at each and every row that's there, or each and every tuple that's stored, and if a match is found, then we fetch it, else we leave it, but then we basically look at all of the records that are there in the table or in the file. The next one is binary search. So this can be used when we are basically searching on when binary search is possible when we're doing an equality comparison on a particular value. So, and if the file is sorted, then a binary search can be done. Another option is to use an algorithm that uses a primary index. So if indexes are provided, then we can use that index, and again, this works for equality comparison. algorithm. So basically do just an index scan and pull out the relevant values. If a hash key is there along with the index, then that helps, that makes it more efficient, and then the selection then happens based on that hash key. So and then there are other methods that further if the selection is not simple, and if there's multiple records involved, if multiple records need to be pulled, then this corresponding algorithms for them, either using a primary index or a clustered index if a clustering index is available. There's also secondary B plus tree algorithm that can be used, again that can be used on equality comparisons. So these algorithms again change based on whether we are doing an equality comparison, or if you're doing a greater than or less than comparisons, or if you're looking for a certain range of values, then accordingly the type of search method that's used behind the scenes by the query processing engine changes. There's also a bitmap index and functional index based algorithms, which then use a different scheme for pulling the relevant records. So all of those were, the previous algorithms were all for simple selection, where there's a simple single rule, but then there could be a situation where our selection involves conjunctive selection, that is where there's multiple conditions with a logical AND, or there's multiple conditions based on a logical OR. So these are basically disjunctive or conjunctive selections, and those then get even more involved. With a conjunctive a selection, we can use an individual index and use the first one and then the corresponding next one, or we could use a composite index. Disjunctive is harder, and it's harder to even optimize, because with the conjunction, you basically, if one of the conditions fails, then we don't have to check for the others, whereas for disjunction that's not the case, and hence all of the conditions in the OR might have to be checked. But again, it's the other way. If one of the condition holds, then the subsequent ones don't have to be checked. But in general, the simpler conditions are easier to handle than the conjunctive and disjunctive conditions. There's also the concept of selectivity. So, and basically that's what gets used by the query optimizer when it's trying to optimize the query plan. So the selectivity is based on, there's a selectivity ratio, which is basically the number of records or tuples that satisfy a condition to the total number of records, and based on that selectivity ratio of a relation, the optimizer might have to vary its plan. Now it also, and this selectivity ratio is basically a number between 0 and 1, where it's 0 when no records satisfy the condition, and it's 1 when all records satisfy the condition. So like I said, for every query, this optimizer has to check and see what the selectivity ratio is going to look like, and based on that come up with a query plan, and it can get the selectivity ratio using the system catalog. So that's all I have in this video. Thank you.